In this video series, we will discuss how to solve Newton's second law problems involving multiple objects. This video series builds on the material covered in my previous series on basic Newton's second law problems. If you find that these video explanations move too slowly, you can use the solutions documents to supplement or replace the video explanations. And you can use the table of contents in the progress bar to skip to particular topics in the video. Now let's try our first Newton's second law problem involving multiple objects. Please pause the video and try this problem. Now, let's discuss the problem together. Here's a summary of the solution for this problem. And now let's discuss this solution step by step. Here are some keyboard shortcuts which you may find useful while you're watching the videos. The problem mentions the concepts of mass, friction, which is a force, acceleration, and tension, which is another force. All of those concepts can be substituted into the Newton's second law equations. So, based on the concepts that are mentioned in the problem, we expect to apply the Newton's second law problem-solving framework to solve this problem. Here's a handout which summarizes a step-by-step method for solving Newton's second law problems involving two objects connected by a rope. There's a link to this handout in the video description box. You should print out this handout so that you can follow along with the steps as you proceed through the video. This problem has already provided us with a sketch, so we begin our solution by making a note of what the question is asking us for. When possible, represent what the question is asking you for with a symbol, or a combination of words and a symbol. This problem asks for the acceleration of the masses. I will interpret this part of the question as asking for the magnitude and direction of the acceleration for each mass. We can represent the magnitude of the acceleration with the symbol A, written without an arrow on top. When you write a vector symbol without an arrow on top, the symbol stands specifically for the magnitude of the vector. The problem also asks for the tension. The professor probably intends this part of the question to be asking for the magnitude of the tension force, which we can represent with the symbol capital T written without an arrow on top. Draw the velocity vector for each object. The velocity vector indicates the object's direction of motion. The problem tells us that mass 1 is sliding down the incline and that mass 2 is falling. So we draw a velocity vector pointing down the incline for mass 1 and a velocity vector pointing straight down for mass 2. Check that the given units are SI units. This problem uses units of kilograms, and yes, kilograms are SI units. Here's a summary of the steps that we've completed so far. This step isn't relevant for this problem because this problem is numeric, not symbolic. Now let's work on the free body diagrams. We usually draw a free body diagram for each object whose mass is mentioned in the problem. So for this problem, we draw two separate free body diagrams. One free body diagram showing all the forces being exerted on mass 1, and a separate free body diagram showing all the forces being exerted on mass 2. Here is a general two-step process for identifying the forces for your free body diagram for a particular object. Let's begin by identifying the forces being exerted on mass 1. We begin this diagram by drawing the weight force on object 1. To complete the free body diagram for mass 1, we systematically ask what is touching mass 1. Mass 1 is being touched by the incline. An inclined plane is the type of thing we treat as a surface. A surface can exert both a normal force and a frictional force, and the problem indicates that there is friction between mass 1 and the incline. We know that kinetic friction applies for this problem because mass 1 is sliding. Are there any other forces on mass 1? Well, ask yourself, is there anything else that is touching mass 1 besides the incline? Yes, the sketch that was provided with the problem indicates that mass 1 is also being touched by the rope. We will refer to the force exerted by a rope as a tension force, symbolized as uppercase T. Are there any other forces on mass 1? Well, ask yourself, is there anything else that is touching mass 1 besides the incline and the rope? No, nothing else is touching mass 1, so there are no other forces on mass 1. Now, let's identify the forces being exerted on mass 2. We begin this diagram by drawing the weight force on mass 2. Always try to use the exact right symbols, including the exact right subscripts. For a multiple object problem, we use subscripts to distinguish the two objects from each other. For this problem, we use 1 and 2 subscripts to carefully distinguish the weight force exerted on mass 1 from the weight force exerted on mass 2. Now, to complete the free body diagram for mass 2, we systematically ask what is touching mass 2. The sketch that was provided with the problem indicates that mass 2 is being touched by the rope. The rope will exert a tension force on mass 2. We use 1 and 2 subscripts to carefully distinguish the tension force being exerted on mass 1 from the tension force being exerted on mass 2. Are there any other forces on mass 2? Well, ask yourself, is there anything else that is touching mass 2 besides the rope? No, nothing else is touching mass 2, so there are no other forces on mass 2. You should now pause the video and memorize this general two-step process for identifying all the forces for your free body diagram for each particular object. The key to this process is to systematically ask yourself what is touching the first object, and then systematically ask yourself what is touching the second object. The purpose of the free body diagrams is to identify the directions of the forces exerted on each object. So, here are the rules for determining the directions of the forces. The weight force always points straight down. The normal force exerted by the surface of the incline on mass 1 will point perpendicular to and away from the surface of the incline, like so. In this problem, mass 1 is sliding parallel to and down the incline. So for this problem, the kinetic friction force on mass 1 points parallel to and up the incline, like so. The tension force exerted by the rope on mass 1 points parallel to the rope and away from mass 1. So the tension force on mass 1 points parallel to and down the incline, like so. The tension force exerted by the rope on mass 2 points parallel to the rope and away from mass 2. So the tension force exerted on mass 2 points straight up. Always label every vector arrow. Drawing vector arrows without labels leads to confusion and mistakes. You should pause the video and memorize these rules for determining the directions of the forces. Here's a summary of the steps we completed while working on the free body diagrams. Now, let's work on the force tables. The purpose of the force tables is to organize the data, which we will need to substitute into our Newton's second law equations. We need a force table for mass 1 and a force table for mass 2. The purpose of the first row of the force tables is to represent the magnitudes of the force vectors. You should know that a magnitude is a number that can be positive or 0, but that can never be negative. A vector symbol written with an arrow on top stands for the complete vector, including both direction and magnitude. In contrast, a vector symbol written without an arrow on top stands specifically for the magnitude of the vector. So, in the first row of our force tables, we write the vector symbols without arrows on top to indicate that these symbols stand specifically for magnitudes. In contrast, the purpose of the free body diagrams is to represent the directions of the forces. So in the free body diagrams, we write the vector symbols with arrows on top. Here is a three-step process for representing the magnitudes of the force vectors in the first row of our force tables. In this problem, we were not given a value for the magnitude of any of the forces. There is a special formula for the magnitude of the weight force, W equals mg. We can use that special formula to calculate the magnitude of the weight force on mass 1 and the magnitude of the weight force on mass 2. There is a special formula for the magnitude of the kinetic friction force, F sub k equals mu sub k times little n. We can use this special formula to represent the magnitude of the kinetic friction force on mass 1. There is no special formula for the magnitude of the normal force, so we will represent the unknown magnitude of the normal force with the symbol n, written without an arrow on top. There's no special formula for the magnitude of the tension force, so we will represent the unknown magnitude of the tension force with a symbol. For a massless rope stretched over a massless frictionless pulley, the magnitude of the tension force is the same at both ends of the rope, although the direction of the tension force may be different at the two ends of the rope. In an introductory physics course, we typically assume that the rope is massless and assume that the pulley is frictionless and massless, unless the problem indicates otherwise. So, the magnitude of the tension force exerted on mass 1 will be the same as the magnitude of the tension force exerted on mass 2. So, we can use the same symbol, capital T, written without an arrow on top, to stand for the magnitude of the tension force on mass 1 and for the magnitude of the tension force on mass 2 in the first row of our force tables. To repeat, for two objects connected by a rope, in the first row of our force tables we can use the same symbol to represent the magnitude of the tension force at both ends of the rope. For purposes of filling out our force tables, we do not try to figure out how all these forces will interact with each other. We can let the Newton's second law equations figure out those interactions for us later in our solution. You should pause the video and memorize this three-step process for calculating or representing the magnitudes of the force vectors in the first row of your force tables. Before we can break the forces into components, we must choose our axes for each object. As a beginning physics student, for multiple object problems, I recommend that you should choose the direction of motion for each object as the positive direction for that object. Mass 1 is moving parallel to and down the incline. So, for mass 1, we choose an x-axis that points parallel to and down the incline. And let's choose a y-axis for mass 1 that points perpendicular to and away from the incline. Mass 2 is moving straight down. So, for mass 2, we choose a positive y-axis that points straight down. And let's choose an x-axis for mass 2 that points right. It's okay to choose different axes for different objects. Now, some professors might prefer to choose up as the positive direction for mass 2, but in my opinion, that's an inferior approach for most beginning physics students. As a beginning physics student, you will probably have better success with multiple object problems if you make it a habit to choose the direction of motion for each object as the positive direction for that object. Always write down your axes for each object. Now that we've chosen our axes, we're now ready to break the forces into components. We can use this rule to break F sub k, n, t sub 1, t sub 2, and w sub 2 into components. Be careful to get every plus or minus sign correct in front of every non-zero component. For example, w sub 2 points down, which we have chosen as the positive y direction for mass 2. So w sub 2y is positive. T sub 2 points up, which we have chosen as the negative y direction for mass 2. So t sub 2y is negative. We chose down as the positive y direction for mass 2, so we have to be careful to remember that choice when we determine the components for mass 2. It's crucial to include the negative signs on f sub kx and on t sub 2y. If you leave out these negative signs, you will get the problem wrong. I recommend that you should include a plus sign in front of each positive component, because that will help you to remember to include the crucial negative signs in front of the negative components. The weight force exerted on mass 1 is neither parallel nor anti-parallel to either axis for mass 1, so this rule doesn't apply for w sub 1. Instead, to break w sub 1 into components, we will have to draw a right triangle and use the SOHCAHTOA equations. Here's a summary of the process for breaking w sub 1 into components. I went into detail about the step-by-step process for breaking the weight force into components for an inclined plane problem in my earlier series on basic Newton's second law problems. Again, be careful to include the correct plus or minus sign in front of each component. We have now completed our force tables. Here's a summary of the steps we completed while working on the force tables. Now we're ready to work with the Newton's second law equations. First, we write the general Newton's second law equations. Mass 1 experiences forces in both the x and the y components. So for mass 1, we write the Newton's second law equations for both the x and the y components. Mass 2 experiences no forces in the x component. So for mass 2, we write the Newton's second law equation only for the y component. Always try to use the exact right symbols, including the exact right subscripts. For a multiple object problem, we use subscripts to distinguish the two objects from each other. For this problem, we use 1 and 2 subscripts to carefully distinguish the Newton's second law equations for mass 1 from the equation for mass 2. Also, we use x and y subscripts to distinguish the Newton's second law x equation from the y equations. If there's enough room on the page, you should write the Newton's second law equations at the top of 3 adjacent columns. Now we can plug specifics into the equations. The sigma symbol means add. So on the left side of each equation, we add the individual force components, which we determined in our force tables. Here we add the x components of the forces on mass 1. Here we add the y components of the forces on mass 1. And here we add the y components of the forces on mass 2. For mass 1, we substitute 3 kilograms, and for mass 2, we substitute 2 kilograms. Now we need to determine what to plug in for a sub 1x, a sub 1y, and a sub 2y. If an object is motionless in a component, then that component of its acceleration is 0. Mass 1 is moving parallel to the incline in the x component. Mass 1 has no motion perpendicular to the incline. Mass 1 is motionless in the y component. So we can substitute 0 for a sub 1y in the Newton's second law y equation for mass 1. There's no reason to substitute 0 for a sub 1x or for a sub 2y. In fact, a sub 1x and a sub 2y are what we need to figure out in order to answer the question. If you choose a positive direction for each object that points in the direction of motion for that object, then the acceleration component in the direction of motion for one object will equal the acceleration component in the direction of motion for the other object. We've chosen a positive x-axis for mass 1 that points down the incline, which is the direction of motion for mass 1. And we've chosen a positive y-axis for mass 2 that points straight down, which is the direction of motion for mass 2. So our axes do satisfy this requirement. So, based on this rule, we can write the equation a sub 1x equals a sub 2y. Then we can use that equation to substitute a1x in for a2y in the Newton's second law equation for mass 2. We can continue to use the symbol a1x in the Newton's second law x equation for mass 1. Remember, this rule only works if you choose a positive direction for each object that points in the direction of motion for that object. For example, if you choose up as your positive y direction for mass 2, then a1x does not equal a2y. So, as a beginning physics student, you will make your life easier for multiple object problems if you make it a habit to choose a positive direction for each object that points in the direction of motion for that object. I'll discuss why this rule works and what happens if you choose up as the positive direction for mass 2 towards the end of this video. Now we're ready to solve the Newton's second law equations. The Newton's second law x equation for mass 1 has 3 unknowns, and the Newton's second law y equation for mass 2 has 2 unknowns. So we postpone working with those equations. The Newton's second law y equation for mass 1 has only 1 unknown, so we begin by solving this equation for n. Our result is that n equals 25.5 newtons. Now we substitute our result for n into the Newton's second law x equation for mass 1. The Newton's second law x equation for mass 1 now has 2 unknowns, and the Newton's second law y equation for mass 2 still has 2 unknowns. So it might seem like we're not ready yet to solve either equation. But when we consider these two equations together, they form a system of 2 simultaneous equations with a total of 2 unknowns, capital T and a1x. When you have as many equations as unknowns, it's usually possible to solve for the unknowns. The most efficient way to solve this particular system of equations is the addition method. Here's how it works. We take the Newton's second law x equation for mass 1, and we rewrite that equation here underneath the y equation for mass 2. Now we can add these two equations. When we add these two equations, the t's cancel out. That's the reason why the addition method is an efficient method for solving these particular equations. Now we have an equation in one unknown, so we can solve this equation for a1x. Our result is that a sub 1x equals positive 4.82 meters per second squared. Because a sub 2y equals a sub 1x, we know that a sub 2y also equals positive 4.82 meters per second squared. Next, we can take our result for a sub 1x and substitute it into the Newton's second law x equation for mass 1. The x equation for mass 1 now has only one unknown, so we can now solve this equation for capital T. Our result is that capital T equals 9.96 newtons. Notice that we arranged our work with the Newton's second law equations in 3 adjacent columns. That helped us to keep our math organized, so I encourage you to imitate this adjacent column approach for your own work with Newton's second law equations. Now we're ready to answer the question. We've determined the acceleration components, but I'm interpreting the question as asking for the magnitude and direction of the overall acceleration vector. We've determined that a sub 1y equals 0, and because mass 2 is motionless in the x component, a sub 2x also equals 0. So, we can use this rule. A sub 1x is positive. The positive x direction for mass 1 is parallel to and down the incline. So the direction of a sub 1 is down the incline, as I've drawn here. Our result for a sub 2y is positive. The positive y direction we've chosen for mass 2 is straight down. So the direction of a sub 2 is straight down, as I've drawn here. Our result for the magnitude of the acceleration is the same for both objects. I'll round that result to 4.8 meters per second squared. I'll round our result for the magnitude of the tension force to 10 newtons. Check to make sure you included units with your answers. An answer without units is wrong. Check to make sure you answered the right question. This question could have asked us about the normal force. Check to make sure you answered all parts of the question. This question asks about both the acceleration and the tension. Here's a summary of the steps we completed while working with the Newton's second law equations. We have one more check left to make. We need to check whether our results make sense. Does it make sense that our results for n and t are positive? Well, the symbols n and t, written without arrows on top, stand for magnitudes. And a magnitude can never be negative. So yes, it does make sense that our results for n and t are both positive. If either of these results were negative, then we'd know that we had made a mistake. Does the size of our result for n make sense? In this version of the free body diagram, I've broken W1 into components. Earlier, we found that W1x points parallel to and down the incline, and that W1y points perpendicular to and into the incline. So in this version of the free body diagram, I draw W1x pointing parallel to and down the incline, and W1y pointing perpendicular to and into the incline. Now, our result for the magnitude of the normal force is 25.5 newtons, which is the same as the magnitude of W1y. Does that make sense? Well, W1y is trying to make mass 1 start moving into the incline. To prevent mass 1 from starting to move into the surface of the incline must exert a normal force that will cancel W1y. So yes, it does make sense that the magnitude of the normal force equals the magnitude of W1y. So in this version of the free body diagram, I've drawn the normal force arrow the same length as the W1y arrow to reflect the relationship between those two forces. Does our result for the magnitude of the acceleration make sense? In this problem, it's interesting to compare our result for the magnitude of the acceleration with 9.8 meters per second squared, which is the magnitude of free fall acceleration. Does it make sense that our result for the magnitude of the acceleration is less than 9.8 meters per second squared? Well, because mass 2 is being held back by the rope, mass 2 is not falling freely. So, yes, we would expect that mass 2 will fall with an acceleration that is smaller in magnitude than free fall acceleration. In our solution, we used this equation, a1x equals a2y. We used this rule to justify the equation. Now, in this part of the video, I want to demonstrate that this rule really is correct for this problem. Furthermore, I want to demonstrate that the rule only works when we choose a positive direction for each object that points in the direction of motion for that object. Suppose that mass 2 is speeding up. Then, because they're connected by the rope, mass 1 will also be speeding up. So, let's suppose that both masses are speeding up. Then, based on this rule, A1 will be parallel to V1, and A2 will be parallel to V2. So, A1 will point parallel to and down the incline, and A2 will point straight down. So, A1 will point in the positive x direction we've chosen for mass 1. So, A1x will be positive. And A2 will point in the positive y direction we've chosen for mass 2. So, A2y will also be positive. Remember that it's a good habit to include a plus sign in front of positive components. Because they are connected by the rope, the magnitude of the acceleration will be the same for both objects. So, we can represent the magnitude of the acceleration for both objects with the same symbol, a, written without an arrow on top. So, a1x equals positive a, and a2y also equals positive a. So we see that a1x really does equal a2y. So, we've confirmed that this rule really does work for this problem. This confirms that we were correct to use the equation a1x equals a2y in our solution for this problem. Now, what would happen if we had chosen up as the positive y direction for mass 2? In that case, a sub 2 would still point down, but now down would represent the negative y direction for mass 2. So with these axes, a sub 2y would be negative. In this example, we haven't changed anything for mass 1, so a1x will still be positive. Because they're connected by the rope, we can still say that the magnitude of the acceleration will be the same for both objects. So we can still represent the magnitude of the acceleration for both objects with the symbol a. So in this case, a1x does not equal a2y. Instead, in this case, the correct equation would be a1x equals negative a2y. This example confirms that this rule only works when we choose a positive direction for each object that points in the direction of motion for that object. Now, as a physics beginner, when possible, it's best to avoid negative quantities in our solutions. So you can see now why it was best to choose the direction of motion for mass 2, down, as the positive y direction for mass 2, to avoid having to deal with this negative sign. Now let's do a recap of our work on this problem. In this video, we learned how to deal with a problem that involves two objects connected by a rope. For that type of problem, we draw two separate free body diagrams. We complete two separate force tables, and we apply the Newton's second law equations separately to each of the two objects. To complete the free body diagram for mass 1, we systematically ask, what is touching mass 1? To complete the free body diagram for mass 2, we systematically ask, what is touching mass 2? The magnitude of the tension force is the same at both ends of the rope. So, in the first row of our force tables, we can use the same symbol, capital T, written without an arrow on top, to represent the magnitude of the tension force at both ends of the rope. As a physics beginner, it will simplify your solution for multiple object problems if you choose the direction of motion for each object as the positive direction for that object. It's okay to choose different axes for different objects. If you choose a positive direction for each object that points in the direction of motion for that object, then the acceleration component in the direction of motion for one object will equal the acceleration component in the direction of motion for the other object. For this problem, we can use this rule to write the equation a1x equals a2y. Then we use this equation to substitute a1x in for a2y in the Newton's second law y equation for mass 2. Again, this rule only works if you choose a positive direction for each object that points in the direction of motion for that object. We used the addition method to solve our system of simultaneous equations. The addition method is often the most efficient approach for Newton's second law problems involving multiple objects. Always try to use the exact right symbols, including the exact right subscripts. For a multiple object problem, we should be careful to use subscripts to distinguish the two objects from each other. For this problem, we used 1 and 2 subscripts to carefully distinguish between the weight force on mass 1 and the weight force on mass 2, and between the tension force on mass 1 and the tension force on mass 2. Again, we used 1 and 2 subscripts to carefully distinguish between the mass of object 1 and the mass of object 2. And we used 1 and 2 subscripts to distinguish between the acceleration components for mass 1 and the acceleration components for mass 2. Notice how different our analysis was for a1y, which equals 0, and for a2y, which equals a1x. Think in terms of components. For example, each Newton's second law equation for this problem refers specifically either to the x component or to the y component. We used x and y subscripts to carefully distinguish between variables that refer to the x component, such as a1x, and variables that refer to the y component, such as a1y. Notice how different our analysis was for a1y, which equals 0, and for a1x, which equals a2y. When you break the forces into components, be careful to get all the signs correct. You should include a plus sign in front of positive components, because that will help you to remember to include the crucial negative signs in front of negative components. In order to break the weight force into components, we needed to draw a right triangle and use the SOHCAHTOA equations. I covered how to break the weight force into components for an inclined plane problem in detail in my earlier series on basic Newton's second law problems. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.